Okay, I'm very happy to have Benny Sudakov here. Tell us about disjoint pairs in set systems and combinatorics and lower end matrices.
Thank you very much. So I want first start by saying that all this is joint work with three brilliant young mathematicians, Zach Hunter and Alexa Milojevic. They PhD students in ETH, and Istvan Tomon used to be in ETH and now in India. And let me start with a basic, very fundamental problem in communication complexity by Lovatz-Escriver. So you have M0, 1, M by M matrix of rank n, and you want to ask how large let me do a notation on M. It's I want a submatrix of a matrix M, which is completely 0 or completely 1. So you're homogeneous. It contains only one value, M prime subset of M max such that M prime is all 0 or all 1. Right? So I want the biggest, right, maximal. So that's a question. Now you observe that because you're talking about 0, 1 matrix and the dimension of the row space is n, you cannot have more than 2 to the n different rows and columns. So the easy bound, easy, is that contained. Sorry. It's a submatrix, right? How you would. Okay. Yeah, M prime. So you want the submatrix of your original matrix, and combinatorial submatrix, rows and columns, such that M prime is all zeros or ones, and you want it as big. Very good. Please stop me if something is
square matrix, M prime?
M prime is square matrix, right? Let's say square. Right? Well, you want it as large as possible, and homogeneous means it's all zeros, all ones, right? So you don't have. And because if your matrix has rank n and 0, 1 matrix, you can have only at most 2 to the n different rows and columns. So you can easily show that you can have at least that large homogeneous submatrix, right? And we always think about n being fixed and m being large, right? So you can have this. But the conjecture of Lovatz and Sachs from 88 says that you can actually find much bigger matrix of size at least n divided by 2 to the logarithm with some power, right? M. Yes. Okay. So this is a conjecture. So this is a really huge homogeneous submatrix. And because this 0, 1 matrices are related to communication complexity, this is one of the central problems in communication complexity. Now, so what we know, we're still very far from proving this result. But the best bound which we currently have is that homogeneous submatrix we can find of the size n divided by 2 to the power squared. And m always, yes, m. Right, I will make sure. I use m here because this n I want to use in other results as well, so it's convenient to have this m. So this is the biggest we can have, and it was a breakthrough by Shachar Lovet, who actually managed to get here 2 to the c squared and log n. And this bound is some refinement which we did together with Istvan Tomon. It's a slightly different approach. This is this result. Okay. So I'm mentioning all this because one of the natural ways to create a combinatorial matrix is to take a cross intersection between two families of sets. So here is a matrix. So imagine you have two families of sets on n elements, right? And both families have M sets, right? So you have two families of M sets on the same ground set of N elements, and then your matrix M is just ground matrix of characteristic vectors. So MAB equals A intersection B, where A is in A, B is B. So this is a combinatorial matrix. It's not a 0-1 matrix, right? I will say things about it. So it's not necessarily 0-1 matrix, it's integer matrix, but it's immediately rank n, at most n, because you're taking right product of the characteristic vectors which live in n-dimensional space. Is this clear? Now, what is very interesting, right? So very recently, which was approved by Tsumian, Lovett, and Shirley, that it's enough to prove Lagrange conjecture. So this is Lagrange conjecture. It says for these matrices, combinatorial matrices, intersection matrices of sets, where A intersection B takes two values, K.
Can you explain why the rank is low?
Because you see, so how you can get this matrix? You can take an incidence matrix of your set. So this is a matrix whose say rows are characteristic vectors of the set and columns are the elements. So it's n by m matrix, and then multiply it by m by n matrix, right? Which is again incidence matrix of the matrix B, and that's your matrix MAB, right? And because of that, the rank is at most, right? And so what is interesting is that they observed, it's actually a proof, it's a very clever proof, but not a long paper, that you can prove, so it's enough to work for Lagrange conjecture only in this what, right? You take these combinatorial matrices where the intersection takes only two values, and if you can prove Lagrange conjecture, if you can find inside them a huge homogeneous submatrices, that's already.
What do we know about K?
So K will come from the problem. You cannot choose K.
I cannot.
You cannot choose K. Because if your K would have been 0 or 1, since this matrix is a positive semi-definite, we actually know to solve Lagrange conjecture for such 0-1 matrices. This is good to remark. So if we have a 0-1 matrix, which in addition is positive semi-definite, which obviously the Gram matrix is, then we know to prove. Here you cannot choose K. But that's actually motivation for this talk. So the main heroes of this talk would be these matrices, right? So I will look on the matrices which come from intersection of two families of sets. Now, Lovett had another conjecture motivated by Lagrange conjecture, which says that if M is 0-1 M by M matrix of rank n with quadratically many zeros. So imagine you have a matrix, and now it's very much more in this direction, right? I only tell you that your matrix has a lot of zeros, constant proportion. I don't tell you anything about other values. Other values can be anything you want. Then he still thinks, right? Then the conjecture says that you can find a homogeneous submatrix. Again, a reminder, in this case, actually, homogeneous would be all zero, right? Let me even write it. They exist all zero.
This is 0-1 matrix, so you meant something
No,
else?
this doesn't need to be 0-1.
So you wrote 0.
Oh, sorry. Yes, sorry. M by M matrix, just rank n, which has delta M square zeros. Then you can find all zero submatrix, M prime of M, and the size of M prime would be n divided by 2 to the constant square root m, right? It's exactly this result. That was the motivation of his conjecture. So conjecture was that because of the tools, obviously you need to know these proofs, he conjectured that just the sheer fact that there are constant fraction of ones already will create you a huge homogeneous submatrix, a matrix whose size is m divided by 2 to the square root n, and we always think about n as a constant, okay? So we still don't know this. But again, since you already saw this, so the next natural step was a problem by Singer and Sudan, which said, okay, prove this at least for these combinatorial matrices, right? Prove conjecture for these matrices, which are intersection matrices of two set systems. So imagine you have now two set systems, each has m sets. You take their cross intersections. You observe that there are many disjoint pairs, a constant fraction of disjoint pairs. Is it true that you can find two large subfamilies, A prime and B prime, such that they cause a completely disjoint? And this is indeed our first theorem, right? That then there exist A prime subset of A, B prime subset of B, of size m divided by 2 to the c squared 10, such that A intersection B is empty for every A prime B prime. So if you have a set system which have a lot of disjoint pairs, with, I need to say, of course, here, with least delta m squared disjoint pairs, then you can find exactly like whatever.
And do you have permanence on?
Yes, so very good, excellent, right? So this is tight, right? And to see that this is tight, just pick A, B to B collection, random subsets of size some constant square, right? So create your families like you're picking sets at random of size square root n. Now observe what will happen if you take two random sets of size square root n with constant probabilities they are disjoint. So indeed you will have constant fraction of all the pairs disjoint. But now if you want to have families which are completely disjoint, then it's more or less you need to prove it that the union of all sets in the first family and the unions of all sets in the second family would be disjoint. Now, if you take the union, one of them occupies at most n over 2 elements. And now if you think, if you're taking a random subset and you want it to end up in the given n over 2 elements, the probability of this, because of factor half, it's 2 to the minus square root. And that's why this is time, okay?
So for the theorem, you also assume the rank is exactly n?
No, I don't, right? Because I'm saying of size at least, right? I'm not saying, right? If it's smaller, it's even better. Right? I don't, right? I really just say rank obviously at most n, but I don't say anything about rank because, right, rank was just a motivation how we at all arrived to this question. But the sets come from the ground set of size n. So the rank is obviously at most.
Yeah, but for the conjecture, the density of the m prime will be relevant to the rank, right?
Right.
So
yeah, right. So that's why I said, right. So that's what I'm not answering this thing. I'm answering the question of Sudan and Singer, who said prove this for this type of matrices, right?
So if the rank of your AB is actually smaller,
Yeah, if it's smaller, then I'm not right. My preview will see that only will reflect this
I
S.
see, I see.
Will not reflect the rank. Any questions? Okay, so this is a problem number one, which I want to mention. Now, actually, the question, so observe, right? So the realm which we're going is again the following. You have two families of sets on the same ground set with n elements, and we're studying something about the disjointness pattern, right? So how many sets can be disjoint? And actually, precisely this question was asked well before the long-run conjecture by Erdős and Daykin in 1981. So they ask the following. So you have two families of sets on n elements, right? Both of size m, and they ask how many disjoint pairs these families might have. I'll give you arbitrary, I want worst case scenario, I give you arbitrary two families on the same ground set with m elements each, and I want to maximize the number of disjoint pairs. If you want, I make this combinatorial matrix and I want it to contain as many zeros as possible. Now observe, let me give you an example. Sorry? Right, so the example is obviously Avi was right, so it's very important to notice that if your families are small, if your m is smaller than 2 to the n over 2, you can have completely zero matrix, right? Because you can take elements in A to be subset from 1 up to n over 2, elements in the family B to be subset of n over 2 up to n, right? This is A, B, B. And then you will have m squared pairs. So if your m is small, if your families are small, you can just take them on disjoint parts of your ground set, and you would be completely disjoint. But the interesting question, right, so the question which they actually ask, what if m is bigger than 2 to the n? So what if you cannot do this example, okay? And so here is a construction which I want to present. Maybe I'll change a little bit the order, and then I'll tell you. Maybe let me first tell you what is known. There are two results, partial results, which were known over the years. So in 1985, Alon and Frankel, 1985, they proved that if your n is really bigger than 2 to the 1/2 plus delta times m, right? Times n. Right? So if you exponentially bigger than 2 to the n, then you really cannot have quadratically many, then you should drop. So your constant in the exponent should drop below 2. Then the number of disjoint pairs is at most m to the 2 minus some constant delta square. Okay. So you really have subquadratically many. And then there is another result which we proved together with Noga, Shagnik, Das, and myself later. Over here. I'm not sure. But if you want to refine this, right? So this is where you really well above 2 to the n. What if you sufficiently close? If your m is bigger than n to the d 2 to the n over 2, And this is a kind of correct parameterization, because if you can be only constant times bigger than 2 to the n over 2, you can still use this example, right? Because you will get maybe not m squared, but you get constant m squared disjoint pairs, right? You don't. But so that's why you want to be really above 2 to the n over 2. And one parameterization you can have is you bigger than 2 to the n over 2 by some power of n. Then the number of disjoint pairs is at most little of m squared, right? It definitely goes to 0 together with m squared, right? This result does not apply because they really needed it to be much. Okay? But this still doesn't answer the question. The question was how many pairs you really can have if I really want to know it as a function of m when I go above 2 to the n squared. Let me give you an example which appears in the paper of Alon and Frankel. So this is the example which I think.
Good question.
Yes, of course.
For the D there, what's the quantification over D?
So this little o depends on this dd. Think about d being constant. Right? This is my just parameterization. I need somehow to tell you by how much n bigger than 2 to the n over 2. And because of the next example, which I'll give you, this is a convenient parameterization you will see in a second. Right? Okay. So here's an example which they gave, which I think they suggested should answer the problem. Right? So the family A, you take all sets A such that A intersect the first half of your elements in at most, and that's why kind of integers comes here, because of course if you give me here something which is not full power of n, I would not have a good example, but for all the sequences you'll see. So I'm taking A to be all elements in your subsets of your ground set which intersect first half in at most d elements. And similarly, I take B, all elements B, which intersect second half in at most D. Okay. These are my family subsets. Now, first of all, let's do some arithmetic. So what is the size? So the size of the family is the following. They're both of the same size, and observe that on the second half, for example, for A, you can do whatever you want. So it gives you 2 to the n over 2. But on the first half, you need to pick at most d elements, which gives you some of the binomial coefficients and choose I, where I is at most d. So this is essentially my parameterization, right? Because the biggest binomial coefficient is n to the d, n to the d, 2 to the n over 2. Now, how many disjoint sets you expect from this family? Now, observe the way to think about it is that if I have such a set A, so I have on the first half d elements, then the set from the family B, if you think about it being random, should avoid these d elements. This happens with probability 2 to the minus d. Because a typical set from family B on this first half would be just a random subset. So you get 2 to the minus d because B should avoid A on the first half, but you also will get 2 to the minus d because A should avoid B on the second half. And so therefore the number of disjoint pairs would be very closely 2 to the minus 2 d m squared, 1 plus little, right? You can do really computation. You can, you know it's very accurate. Right? So this is answer. Okay? And so the nature of conjecture is that this what's the best construction. right? And our second theorem kind of proves asymptotically this result. So what we know, we have two statements. The first statement is that if M is indeed of the order n to the d 2 to the n over 2, then maximal number of disjoint pairs and d constant, maybe let's say d constant for a second. Right? In this example, d doesn't need to be constant, and I will remark on this. If d constant, then the maximum number of disjoint pairs is at most 1 plus little of 1, indeed 2 to the minus 2d m squared. So in this regime, the result is very accurate. We don't know, I mean, one can conjecture, and it might be true that this is really the best example. But that, of course, we don't know, but we can come really very close. So we know that this example is even tight, and even tight up to a leading constant, right? So this is the best way to create the maximal number of disjoint pairs if the families are very close to another. And the second,
Something,
yes,
short question.
Of
Like
course.
in your result with Noga and like the ADS one, the little o is parameterized by d.
by d, right? So it's so this little o parameterized by d, it's something like 2 to the minus some constant times d, but you see, right, this constant nowhere tight close to, right? So we didn't then getting information about how the families look. Yeah. But so we realize that that's a kind of a right parameterization, but this is actually results.
So now this is a strengthening of your like.
Yes, absolutely. Because this is right. This is in this regime. This completely solves this, unless you want really characterize it precisely.
Yeah.
Now the second thing, if M has this interesting, this what happens for a long Frankel regime. So if M is of the order 2 to the 1/2 plus delta times n, then number of disjoint pairs is at most, let me write it, and I'll tell you what it is. It's m to the power 2 minus some constant delta divided by log of 1 over delta.
That's it, yeah.
Yeah, that's,
Yeah.
I think that's it.
This is instantiating the.
Right, this is precisely this estimate, but of course now so if you choose your d, right, so maybe let me say from where it comes. So let's choose your d such that n to the d is 2 to the delta m. Then your d should be of appropriate size. It should be of size linear in n with this with this coefficient, right? So if you want. So maybe let me write it here. So if you want your n to the d to be 2 to the delta n, then your d should be roughly delta n divided by log 1 over delta, right? And therefore, that's precisely because of this result, what you're expecting to lose. Unfortunately, here, I don't know what this constant should be, right? I don't know it that accurately. Right? I know now more quantitative behavior. The quantitative behavior is correct. It's not delta square. It's this, whatever comes from example, but here there is much more things left to be done because we don't know that this is the correct answer. Is this clear? Right. But so this is again very interesting example, which looks pretty complicated. But this is the truth, right? So this is how you create the most number, right? You create the biggest, the densest combinatorial matrix in this form, this
No, this is the only example.
No, even that I don't know, right? So I think the strongest I know is that this is example is asymptotically tight in this regime, but you will see from the proof, I get some information about how the extremal example look like, but I need to work really hard to get it because you'll see the proofs are so some proofs which I'll show you are probabilistic, which should appeal to some people in the crowd, even if they're not combinatorialist, and they're pretty short, right? So I'll tell something about some of the proofs, right? Not maybe of this result, but about the other results.
The first result is related to the Baba et al. Paper where they prove that disjoint matrix for product distribution has a square root n communication complexity.
It's interesting. It never occurred to me to look. I will.
The proof is basically.
So you would be able, once you see I'll show you the proof. Once you'll see it, you'll be able to comment. It's very, very interesting. Yeah,
because it's not a follow from this, so it's right. It's just, I think the argument
should be similar, right? But somehow, it didn't occur to me. But I would assume that Madhu kind of should have been able to make this connection, but but maybe not, right? I need to look, right? If it's related, but I'll show you the proof, right? Okay. So the reason why I'm mentioning this result, because the proofs are very related, and so let me mention the third result I'm going to prove, which is somewhat in this category, but slightly different, and it's related to the very old problem in coding theory, right? So let me start with a definition. You have a family again. Right, it's all would be about combinatorial families. You have a family of subsets of an element set, and you have a parameter R, which think about it as constant, and F is R cover free if no F0 is if you don't have this. So maybe let me explain what I mean. Right? If you don't have if you don't have R sets, which union contains another set in your family, right? So this is very natural from the coding theory kind of motivation. So your family is called R cover free if no set is a subset of the union of R's.
So for R equal 1, it's an anti-chain.
Yes, for R equals 1 is an anti-chain. And obviously the equation, and this is equation which goes to 60s, I think by Singleton and Cowles. 60s. So what is the maximal size of such family? How big it can be? So, looks very innocently looking. Surprisingly, we still don't know the answer for this problem. Right. So let me tell you what we do know. So let me tell you, and then it's so the lower bound is of order n divided by r square, and the upper bound is actually r to the power. So this is c prime, this is c n divided by r square, right? So you see, we don't even know the exponent correctly, right? Because here it's 2 to the n of r square, here it's 2 r to the r square. So how you can get this bound, I can tell you it's very simple. So you take a random subset of size n of r. Now you observe that any two of them intersect because they're random in n over r square elements. And if you choose your constant correctly, this intersection is so small then even r times this intersection cannot cover the full set, right? Because n over r squared times r is precisely n over r, which is the size of your set. And then you look what is the probability. Obviously, you want that any two random sets have a correct intersection. You look what is the probability that how many such sets you can get, and you get precisely n over R squared. An upper bound is actually more sophisticated. By now, we have a really very short proof, but it took some number of years to simplify. Okay? So this is the original problem. Now, the question which I want to address is a
Something bothers me,
yes,
there's an n squared on the left and an n on the
n
right.
squared, n. Sorry, n. Right, because it's a family, right? Very good. So please, please voice your concerns, because occasionally I make typos. Right, so it's obviously right, because the biggest family is 2 to the n, and you just want to see how much. And exactly what Avi said, that if R equals 1 is an anti-chain, and then we know the answer. So then it's a famous Sperner lemma, which says that if you have a collection of sets such that no one is a subset of another, then the maximal number of such sets is precisely n choose n over 2. And it's really, that's why people care about it. It's a very important result. It has application to random matrices and so on, right? So the size of the maximal anti-chain, but then we know, right? It's precisely, right, this right 2 to the n, up to lower the 2. Any questions? Now, the question which I want to address is the question of Alon, Gilboa, and Gueron. And they said the following. So imagine now, so they were motivated by this. Imagine mu is arbitrary distribution over subsets of n elements. So you take your parallel distribution over subsets of an element set, and then you do the following experiment. You choose F0, F1 up to Fr according to mu.
How many do you put in?
No, you have a distribution, right? Distribution just assign weight to every subset. Not to elements, to subsets, right? Right. So this is very important. You have a distribution over subsets of n element sets. Now you sample R plus 1 sets according to this distribution. Distribution is yours, right? You can choose it. Right? And what I want to minimize the probability, right? Minimize the probability that F0 is a subset of union of Fi, I runs from 1 to R. Right? And I want to ask how small this can be. Right?
So that's overall distribution?
Overall distribution in the world, right? So just weighting of subsets. Right? So that's
there are any copies of mu.
sorry?
It's independent copies.
Independent copies, very good question. Right. It's absolutely independent copies, right? Independent. So that's what they asked. And they observed, right? So the theorem and probabilities that it's exact still in the setting subset of union of Fi, I runs from 1 to R, is at least R to the power some constant n over R with a C. So it's R to the power n over R. Now this is, so this is the result. So let me just put it in the context. This is very closely related to this bound. It really comes from this bound, because what you can do, if you give me a distribution such that this probability is very low, what I can do, I can construct for you a R cover free family. And how I will construct? I will sample sets from this distribution, and then I do deletion method. So obviously there would be some example of R plus 1 tuples where one set is the union of another, but because the probability is very small, there would be very few such R tuples. So I would be able to delete them, to clean the family, and then beat this bound. So I will get a construction which improves over the upper bound. Okay, so that was the result, but obviously they didn't know that this is a tight answer. And of course, if we knew solution to this problem, right, if here we would have something better, they could have improved the result. But the last theorem which I want to present is a solution of this problem, which shows that the probability, again, is always at least 2 to the minus some constant n over r, and this is tight, this is answer. Right. So it's actually very interesting. I'll explain in a second why it's tight. It's only one directional connection. So if I would use here beta bound, then I could improve this bound. But unfortunately, the fact that we know to solve this problem doesn't allow us to go back and solve this famous problem. So we don't know to improve this constant. It doesn't work the other direction. But here we know. So again, if you give me arbitrary distribution of subsets of n element sets and you sample r plus 1 sets from this distribution, then the probability that one set is inside union of the remaining set is 2 to the n, roughly 2 to the constant n over r. And the example is that you can take your sets just according to binomial distribution. So probability of given set, you choose some p, I take you in a second which p to take. It's p to the a, 1 minus p m minus a. And once you decide that this is the distribution you take, the best p, or roughly the best p which you want to take is 1 over r plus 1. If you take your p to be 1 over r plus 1, this thing is easily computable, and you see that this is the answer. Okay? Any questions? Right, so these three results which I want to present. So, and somehow the third one is a little bit different flavor, but you'll see the proof is basically once you understand this proof, you can go and do various things about the other, right? So the two results which I'm going to prove, I start with this result because you'll see this have very short proof and an actually very nice proof. It's, you know, like in mathematics, we know for many, many years that sometimes giving the right definition kind of can solve completely the problem. And you see, so there's a one-line definition when what should give, which immediately gives the problem. Then we can use this result to prove this result about homogeneous submetrics of these combinatorial matrices, because it would be the same. This bound is a bit more complicated. It uses the same ideas, but I need some properties of entropy, so it's a more involved proof. This I will not show. Any questions? So maybe then let's start. So I want to talk first about this result. So what I have new distribution on subsets, right, of n elements. So again, right, so every subset of n gets the weight. Okay. So the crucial definition would be the notion of bad set. So a subset of your ground set is bad with respect to this distribution.
You were not asking if it's similar to the Babai-Simon paper. I'll just tell you that I remember very little. But
I will look.
I'll tell you before I see, so I would not be biased. So here I remember that they came from the, I mean, you want to say that the distribution is concentrated on a set of small size. Because otherwise you can cover almost the whole universe with a few disjoint sets.
Sounds in this direction, but I think it's a very similar, I think, but you will see we kind of can streamline this approach. So we need just one concept of bad set. So what does it mean that the set U is bad? So U is bad that if I take all subsets of U, right? U is a set, so I can look on all subsets of U. Each subset has a probability to appear. I add all these probabilities. This probability is small. So this set is, say, 2n over r. Right? So we have our r. So it's exponentially small, and the probability is that it's 2 to the minus n over r. So this is a set is bad if probability to end up, right? It's a very simple definition, to end up in this set if I sample a random subset according to distribution mu is very unlikely. Okay.
And R is the size.
R is this R that I'm choosing, right? That I'm choosing R set. So think about R being given from 3. So the first lemma which I prove is that it's very natural from this distribution. So if I take F1, F2 up to FR, subsets of 2 to the n, independent according to mu, probability that their union is a bad set is tiny, it's minuscule. Probability that union of Fi, I runs from 1 up to R, is bad, is at most 2 to the minus n. It's really tiny. Okay. So let's see this proof. I claim it just one line. It's basically just this definition. Right? So I say probability that union of Fi, I runs from 1 up to R, is bad, is at most. I go over all bad subsets in my universe. I don't know what they are. Sum over all U. U is bad, right? And obviously, this is at most probability that every Fi which I choose, subset of U. Right? And because these are the independent trials, right? I every time choose a new set, I can put here product. So I go over all potentially bad sets and I do something weak. I will not tell you that you equal to the set. I just tell you you end up in this set. Right? So this is this. But now we know, right? Because of our definition of bad U, probability for one trial to end up in U is this. This is the definition, right? This is exactly the probability that I sample a random subset according to mu, I will end up in the set U. So therefore, this is at most. The number of sets U, I don't know, but I would not care. I put 2 to the n. This is a number of U. But because U were bad, probability to end up in U for one set, it was 2n over R. And I'm doing this experiment R times. Now, obviously, I will get 2 to the minus 2n times 2 to the n. So this equals 2 to the minus. So this is a very, very simple scheme. But now let's see why it immediately implies this conjecture of Alon, Gilboa, and Gueron. Because this is all what we need, this lemma. Okay? So the proof of theorem, let's call this theorem 3. So I now do this experiment. So I choose random independent copies of F0 and Fi according to some distribution. So probability that F0 is a subset of union of Fi's, I runs from 1 up to R. Sorry, from 1 to R, is definitely bigger or equal that probability that the union of these FIs I runs from 1 up to R is good. Intersection with F0 being subset of the union. Obviously, this is a small event, right? So if I want this, but I'm intersecting it with the fact that this is good. Okay? And so this equals probability that F0 inside the union of FIs, conditions that the union of FIs is good, times probability that the union of FIs, this is just a simple conditional probability. But now we're done. So what we know? We know that this happens with probability almost 1. So the probability of this is at least 1 minus 2 to the minus 7. But now if you condition that Fi is good, again, it's a definition. If I know that the something is a good set, if you pick your F0 at random according to distribution mu, the probability that end up in the set is this. This is like a definition of good set. It's bigger or equal than this number because, right, observe that set is good means that some of the mu I, mu A, u is bigger or equal to 2 to the minus 2 of R, right? It's the opposite of bad. So therefore, this probability, this conditional probability, if you know that this set is already good, is 2 to the minus 2 of R. This is essentially one that gives you the proof of the first result. Any questions? Right, so as I said, so basically the correct definition here allows you very naively to prove this lemma. Once you have this lemma, you understand that the only event you should look at where the union of these random sets, it's a good set, and if it's a good set, then by definition it will contain a large fraction, large weighted fraction of the substance.
Can you explain that inequality out there?
Yeah.
Right. Can you explain it again?
Yes, so I'm asking, what is the probability that union of FIs is bad? I'm saying, let's do the union bound. You go over all bad sets U, and you ask what is the probability that the union is this U, right? But now you observe that probability that the union is this U, it's a weaker, so a weaker statement is that U contains all the FIs. This is definitely an upper bound. Now U contains all the FIs, but the FIs are independent copies. So it's like a product of probabilities that every FI is inside U. But this is a probability that Fi is inside U upper bound because U was bad. And the number of potential sets is 2 to the. Yes.
So when just to clarify, so the C in theorem 3 is actually 2, no?
It's actually 2, and if I walk, I prove this lemma in a bit wasteful, yeah, in a wasteful way because I want to use it for the next thing and not to prove it again, but I actually can make it 1.
Oh.
But we still have gap. I don't think that it gives you 1. I think again, you can maybe, by looking, this proof is very naive, right? Very short. You can try to go and understand what is the best distribution. But it's a more complicated question. We try a little bit, it doesn't seem, you don't get it cheaply. Yes.
For the Bernoulli, what do you get for C?
So what I get here, something like e to the power n over r, I think. Right? Because it's exactly like you want everybody to, right? You want F0 on the B. If somebody contains 1, you want F0 also to contain 1, right? Right? So if F0 contains 1 in some position, you want at least one of the FIs to have 1 in this position to contain a union. And probability that they don't have 1, it's 1 minus 1 over r plus 1 to the power r. This gives you e, and this gives you e to the power n. So that's roughly the back of envelope computations. Yeah, so we don't get 2, we get something like e to the power minus n over r as a lower bound. And therefore there is a gap. Any questions? Okay, now let me finish, and I have time, and I would be tiny bit more sketchy, but not very much. This answer to the question of Sudan and Singer, right? All right, so we have these families A1 up to AM. This is family A. We have family B, have B1 up to M, right? And then we know that delta M square pairs are disjoint. And then I want to show you that I can find a large subfamily here and a large subfamily here, so they would be completely disjoint, right? And the experiment is the following. So let's fix, I want to use this lemma which I have here. Let's fix my R to be square root n, right? So I would be using this thing, right? This lemma. So this is the important lemma which I'm going to use. And let's fix mu to be a uniform distribution. And now you see why I mentioned these two results. And so what I'll do, I'll choose square root m subsets of A uniformly at random, right? Choose maybe A. Like with slight abuse of notation, right? It's not this order, A1, A2 up to AR, random sets in B uniform distribution over A, over elements of A, family A. Not over all subsets, but obviously you put 1 over m on every subset of which is element of A, and you put 0 otherwise. And this is very important that I know this for any distribution. So you take a uniform distribution over or only of these sets. So I choose R sets randomly and with repetition. And let's take U, a union of AI. I runs from 1 up to R.
So when you clarify that theorem?
Theorem, yes, very good. So let's remind the theorem. Theorem says that if I have two families of sets with constant fraction of disjoint pairs, then they exist A prime in A subfamily, B prime in B, both of size m divided by c squared root n, such that every A intersection B is empty. Sorry, A intersection B is empty for every A in A prime and every B in B. So you can find really, so like if you think about this combinatorial matrix, so this is exactly Lovett's conjecture. This matrix has rank n. This matrix has quadratically many zeros. And now you want to find a submatrix of this matrix, but of course, this is a particular combinatorial matrix, which is exactly Sudan and Singer's question, which is completely zero. And so what's the idea? And the idea, if you think a little bit, once you have this lemma, it's not very surprising. So you pick R sets from your family A uniformly at random. You take the union. And R is precisely would be square root n because this is what I want here, right? So if you think about this bound there of probability, you'll see why I'm choosing R. And so the event E1, so event E1, so this is a probability event, U is good set. So So observe what it means. It means that I can define you, if this happens, I can define you family A prime, subset of A. This is family of all A in A, such that A subset of U. Right? So once you define me this union, you can go over all sets in your family A, and everybody who end up in U, you take as your family A prime. And if event E1 would imply that this family A prime has size precisely m divided by 2 to the c squared. And because probability, the good means that the fraction of A inside U is 2 to the minus c squared.
At least.
At least. This is exactly the
Also
difference.
here at least, right?
Yeah, at least. Right. So this is a natural event to deal with. Okay. Now, very good. So now let me define event B. Event E2 is the following. So think about this as a graph, right? So you have a disjointness graph. So where vertices are two sets of size m, these are your sets. And every time the sets are disjoint, you put an edge. So, right, your disjointness graph has constant density, delta density. So now if you take this, right, event 2, if you take a common neighborhood, and I will explain what I mean. Which is all sets being B, which is joined from each. Right? So now once you define me the set, look on all B's which are disjoint from everybody. Now if they disjoint from everybody, they disjoint from the union, right? So the event, which I want to say here, event in 2, is that the size of this delta to the r times m. Now delta is a constant. Now observe, I claim that, right, this is a very natural thing to expect because you have a disjointness graph. You have a graph whose density is delta. If you pick a one vertex at random in this graph, it will see delta fraction of other elements in B which are disjoint. If you pick 2, by convexity, you expect delta squared. If you pick 3, you expect delta cube. If you take R, you expect delta to the R. And to be kind of on the safe side, I will in a second explain, let me put 2 here. But observe this is also basically 2 to the some constant which depends on delta minus square root n times n. So this is event E2. Now if both these two events happen, I'm done, right? Because I take these random elements A, then I take their union, then I look on all elements from my family which contain in this union, and because event A1 happened, I know that I got many. Then I look on the B's which are disjoint from all of them. Obviously, because they disjoint from all of them, they disjoint from U. So therefore, they would be disjoint from this family A prime. And now I'm telling you that there are, again, 2 to the minus square root n fraction of such sets. Then you got these two families. And the only thing I need to justify you is why these two events happen simultaneously. And the short reason for this is the following. So observe that this common neighborhood of A's, as I said, so this convexity is very easy argument. So if you have a graph where the average degree is delta fraction of the whole, the common codegree of R vertices at random is delta to the R. Now, of course, it happens with certain probability, but observe that I know that events that A is good happens with probability very close to 1. Is such as close to 1 probability, it only fails on 2 to the minus n. So I only need to show you that if I have a random variable whose expectation is delta to the r times n, the probability is that it's smaller than half of its expectation, bigger than 2 to the minus n. And the reason for that is very simple, because obviously, of course, your random variable can be very concentrated on the big values, but the biggest values this can be is 2 to the n, right? Because we're living in the world of subset. So if you put all this together, you'll see that even if everywhere on some small set it's 2 to the n, it cannot be, right? It would not be enough to get this big expectation. Right? Think about it. If I put here 2 to the n, but I'm putting it only on 2 to the minus n fraction of my space, it contributes me 1 to expectation. So expectation should be big elsewhere, and therefore these two events intersect. Therefore get the result. Okay? And I think I'm already lost time.
Oh, wow, okay. Oh, thank you.
Can you de-randomize one of the two parts? No.
So I think this part is very easy to randomize, right? This thing, I need to think, it's not clear, right? So this distribution, I need to think, I don't see it right away because this distribution have huge, but you can have really a lot of sets, right? So yeah, I need to think. I didn't say about it. Obviously, probably, maybe you can, right? Maybe because this part is really very simple. This you can download.
So I guess the motivation for this question, or what the Singer and Sudan's question, was log rank. Like
this was not log rank, but this other conjecture, right? So it's a very natural conjecture. Look, all these things from combinatorial point of view fall into something we call Zarankiewicz problem. You have a bipartite graph, and you want to ask where in this bipartite graph you find a complete bipartite subgraph. Or you have a combinatorial 0-1 matrix, exactly like Lovat's-Sachs question, and you want to find a large homogeneous submatrix. And under certain condition on your matrix, you want to say that you can find a large homogeneous submatrix, right? So Lovat's conjecture says that if rank is small, this is your condition, it's just enough to have a lot of zeros, right? It's not enough for log rank, but he thinks that whatever we can currently prove for log rank, you can prove under much milder condition. Right? Obviously, zeros and ones are interchangeable. And so therefore, if I would have knew Lovat's conjecture, I would get 2 to the m divided by 2 to the constant square root n bound for log rank conjecture immediately, right? Just because half of the entries are the 0 ones. Right? So that was motivation. And it's kind of leads to very interesting mathematics, right? So, but I don't think there is any other motivation. From my point of view, this disjointness graph, it's a very natural thing, and I think you guys had a maybe talk also about disjointness graph very recently. So it pops up in various settings, and you want to understand what's going on, and that's a very natural question. What is the Zarankiewicz problem for disjointness graph? And we know to solve it now very accurately.
Do you think you had this problem with the k and k plus 1?
Right.
Do you think that's accessible in any?
Nah, because there you don't know what. Yeah, no. We thought a little bit. Actually, that's how we started, right? That's how we started to think about this question k plus 1 even before the paper of Lovat and Bartsumian and the Sudakov clearly was known. So this was a very natural question which actually appears in all surveys on log rank. And they later said that actually this is log rank, but you don't need, it's even not an approximate question. You can, if you can solve it, you can solve log rank. And obviously we did solve it, otherwise I would have given a different talk today. But then we got to this combinatorial question, and then from there, it actually was the order in which I gave the talk is precisely how we thought. We first solved this question, then we realized that actually we solved this question. And I remember that I worked this question of Erdős and Daykin. And then once we start working on this, we realize that that's what we're doing. We want to take random sets. Then we discover the question of this paper of Alon, and that's the direction.
So is this conjecture of Lovett sharp? I mean,
Yes, yeah, right. I gave you the example because if you take sets of size square root n at random, any two of them disjoint with constant probability. But now if you want to create disjoint families, it's really easy to show that they need to live on different universes, on different ground or parts of the ground sets. And one of them is small, smaller than an over 2. Now, if you pick sets at random, think you're picking every element with probability 1 over square root n. To hit this set, the probability would be 2 to the minus square root n. And that's why it's sharp. Yeah, so the nice thing about Lovett's conjecture, it's absolutely sharp. So we will prove it.
so is that why he gets stuck at square root n in his
And if you need to know our proof, and very similar to Lovett's, would do some things differently. It's a little bit discrepancy proof. So you're finding sparser and sparser submatrices in your matrix, but you're really not using so much that it's 0, 1. You're using much weaker conditions. And that's why he makes this conjecture. It looks like what you're doing, you're really mostly working with either 0 or 1. Yeah, and that's very nature of conjecture.
Yeah, the generalization of Lovett's bound by Barak, Professor and Sam Hopkins, which proves a similar bound like fraction 2 to the minus square root n for arbitrary matrices. There's some other condition, but anyway, that's a significant generalization of Lovett's bound. This motivation comes from quantum information.
I see. Okay. But I think it's also right. I agree. We thought that yes, but I think combinatorially also it's very natural because I said it's a Zarankiewicz problem in certain sense.
Okay, great. Thank you very much again.